Our speaker for today is Jacob Johnson. Jacob graduated with a Bachelor of Science in Physics from the Georgia Institute of Technology. While at Georgia Tech, Jacob worked in the Fusion Research Center, utilizing computer code to study the transport within tokamak reactor plasmas. After graduating, Jacob came to EMA, where he has been for the past 2 years. During his time at EMA, Jacob has used the experience he gained at the Fusion Research Center to expand the plasma-based capabilities of EMA's tools. Notable developments include the coupling of Ansys Charge Plus with Ansys Fluent and expansion of the discharge capabilities to include the breakdown of any gas. Without further delay, I give you Jacob Johnson.
Thanks, Matt, for that introduction, and thank you to everyone else here for joining us today. So without any further ado, let's go ahead and dive into it. Before we can even dive into talking about discharges, though, we should first understand why discharges and plasmas in general are important to us. And the reason for it is because the number of use cases for them has grown drastically over the last few decades. And so some common and notable use cases are going to be for switch breakers and overvoltage protection, like what's shown in the top right here, as well as electric discharge machining, shown here in the bottom right, which is a high tolerance machining process. There's also ionic wind devices that use plasmas to generate wind, which can be used for cooling or other applications. There's also plasma-enhanced chemical vapor deposition, a semiconductor manufacturing process which utilizes plasmas to improve the efficiency of the manufacturing process, as well as many more use cases. It feels like every month there's a new use case for plasmas. But an overview of what's to come, we'll first just briefly covering our electromagnetic and fluid solver, as it'll be important to understand how the plasmas might interact with those solvers later on. And then we'll actually start talking about the plasmas themselves. We'll cover the different kinds of plasmas as well as how we solve them. Then we'll move on to discussing reactions, which are one of the main ways of getting the plasma to interact with the other solvers. And we'll cover how to understand the reactions, how to interpret them, and also what information is going to be useful from those reactions. And then, which is going to be tied into our next section, which will be covering how those reactions will update the plasma quantities and also the quantities in the other solvers. And then we'll finally finish everything off with some examples to demonstrate the capabilities, and we'll also cover some other capabilities that the tool can address, as well as future work. So starting off with the overview of the solvers, this is going to be very brief here, but we construct a set of continuity equations for both our electromagnetic and our fluid solvers. The electromagnetic continuity equations are shown up here, and this is for our full wave solver. These equations are then converted to a matrix form, which are solved using what is known as the Galerkin method. And we are solving for the potentials, and then we get the fields from those, the electromagnetic fields from those potentials. And then here in the bottom, we have our fluid continuity equations. You'll notice we have 3 of them, one for temperature, one for density, and one for velocity. These are the simplest forms of these equations. Correction terms can be added to them to account for compressibility and or pressure gradient if the user desires those terms to be included. And on the right-hand side of these equations here, on the fluid continuity equations, you'll see are the source terms for each one. And so this is going to be one of the ways the plasma interacts with, or this is the way that the plasma interacts with the fluid, is we will use the reactions in the plasma quantities to compute source terms for these fluid equations. And then for the electromagnetic side of things, plasmas are going to possess some conductivity, and so they're going to play a role as far as that is concerned, and then of course they will also generate their own fields. But let's go ahead and get talking about plasma, since that's what we're all here for today. So there are a lot of different kinds of plasmas. And we can generally break these down into three broader categories. The first one being discharges, and these are going to be high density and low temperature plasmas. We also have our space-based plasmas, which are typically low density and high temperature, with the one exception to that being the low Earth orbit environment, or the plasma that's in that environment. And then the third category is fusionable plasmas. And these are going to be both high density and high temperature. Now, unfortunately, given the very wide range of densities and temperatures that a plasma can possess, there is currently no solver available that can simulate all of the plasma types. In particular, the fusionable plasma region, which is shown on the top right of this plot here, that is the region in which solvers tend to struggle with the most. Fortunately, Charge Plus has shown success in simulating both discharges and space-based plasmas. So it's going to be this region shown in the red outline here. And since we're interested in primarily discharges here, we'll kind of focus in on the discharges. And when you're looking into discharges, you might see a couple of different terms thrown around that are referring to different types of discharges, such as glow, corona, arc, and dielectric barrier. There are also some others as well. But the physics involved in all of these discharges is more or less the same. The main difference between them all is really going to be the initial conditions, or just properties of the system as a whole. So, for instance, here I have some images. We can kind of relate everything to the arc discharge, which is shown here in the middle. This is when you have a discharge that actually fully connects your two electrodes and shorts the circuit. And so some of the other types that we have, so like corona discharge, for example, which is shown here at the top. This would be like an arc discharge, except it's not able to make it to the ground. Most cases because it's just too far away. And so instead of having this full discharge, you instead get this just kind of local discharge, partial discharge. And again, that's just because the ground was so far away, it just couldn't make it to there. And then on the other hand, glow discharges, you can get, it's actually pretty similar, very similar to an arc discharge. Main difference here is going to be the initial density in the gas that you're breaking down here. But regardless, the main point I'm trying to get is the physics between the different types of discharges is going to be the same, more or less. And so now we can start talking about how plasmas can be solved in general. And there are three overarching methodologies for solving the plasmas. The first one, which I tend to call the microscopic approach, will actually track each individual plasma particle and evolve it according to, or transport them according to the Lorentz force shown here. And this methodology is the most accurate because you are simulating each individual particle, but as you might guess, it is prohibitively expensive. And just to give you an idea of how expensive it'd be, you would need more time than the universe has existed for in order to simulate just a single time step. So very expensive. And the next methodology that we have is called magnetohydrodynamics, or MHD for short. And this approach will treat the plasma as a fluid. And so the transporting equation in this case is going to be the Navier-Stokes equation. But the Lorentz force does still show up as there's going to be a term in the Navier-Stokes equation to account for it. And this methodology can be solved in a reasonable amount of time, but it's not the most accurate. In particular, it really tends to struggle with electrons, simulating electrons, since they are moving at very high velocities. And so there's problems with both of these two approaches, whether we're talking about computational expense or accuracy. And so Charge Plus adopted a method which is called kinetic theory, which tries to get to the middle ground between both two approaches that I just mentioned. This methodology, the way that we implement it, is called particle in cell, or PIC for short. And even though I say that this is the plasma solution methodology used by Charge Plus, our fluid solver is also able to work as a very rudimentary MHD solver. However, most of the development in terms of plasma-specific things has been done on the PIC. And so for kinetic theory, the basic idea is you want to group all of your particles into what are called macroparticles, and all of these individual macroparticles are then transported according to the Lorentz force, like with the microscopic approach. And this transport is consistent because if we go back a slide here, when you solve for the transport from the Lorentz force, the only particle-dependent quantity here is going to be the charge divided by the mass. And when you group together like particles, this ratio remains the same regardless of how many particles you add, because they both increase by the same factor. And in order to properly be able to simulate everything, you can't just group these particles together and transport them according to Lorentz force, but you also have to account for some continuum physics, particularly when it comes to reactions. And so the whole point of this is you want to be able to characterize the behavior of all of the individual particles contained within a macroparticle. And to do so, we utilize what's called a distribution function, which tells you that if you have a group of particles with some temperature, what the spread of the velocity of those particles is going to be. And so here's an example of it. And so you can see here how we have velocity on the x-axis. And so all of these lines are for different gases, all initialized at 300 Kelvin. And you can see on the y-axis here, this is the probability of finding a particle at that velocity. And so this is the distribution function and how it can be understood. And if you wanted to relate this to the temperature of your group of particles, well, you'll recognize that there's going to be a most probable velocity, the one with the highest probability here, the peak, and that most probable velocity lines up with what the temperature is. So if you were to compute the temperature just from the most probable velocity, you would see that it matches up with the temperature that you are measuring. And so there are many ways that the PIC solver can influence the other solvers. As mentioned previously, your PIC particles can generate their own fields, which can be added to the fields produced by the EM solver. Their PIC quantities are also used for the reactions, which can update the PIC solver itself, as well as the fluid solver. The PIC particles will also have a conductivity associated with them, which can be computed and sent to the electromagnetic solver. Similarly to this, they can also locally reduce the electric field through what is known as charge limiting, where at a sufficiently high density, the charges will shield the potential and prevent it from propagating further into the plasma. And then also, the PIC particles can interact with solids to produce secondary electrons. And so now we'll start going over our reactions. And so here, starting off with some common conventions and some basic information. Energy is a very important quantity to us when it comes to understanding and characterizing reactions. And there's two different ways you can actually describe the energy of a group of particles, but both are related through this equation here, where we have the average particle energy being equal to 3/2 times Boltzmann constant times the temperature of that group of particles. And also, when we talk about both energy and temperature, a common unit we'll use is the electron volt, or EV. This unit is used just because it provides a reasonable size number for the energies and temperatures of interest to plasmas. If you wanted to use Kelvin for the temperature, it'd be too large, and if you wanted to use joules for the energy, it'd be too small. But EV is a very nicely sized unit for plasmas. And the unit itself is actually an energy unit, and it's defined as the potential energy possessed by an electron on a 1 volt potential difference. And so when we use it to describe the temperature, like we say the temperature of this plasma is 1 eV or something like that, we are really saying that the quantity of the Boltzmann constant multiplied with temperature, that is what is equal to that 1 eV. So that is something to keep in mind as we continue our conversation. If we ever bring up a temperature, saying a temperature is some number of EVs, we're saying that the Boltzmann constant times the temperature is equal to that number. And so for the actual kind of basic information on the for the reactions themselves, we can generally write our equations into one of these two forms up here, where we have two particles coming together to interact to not have a change in it. So like these particles are still going to remain after the reaction. And then we'll also have this energy term here. Sometimes you won't see this written down in chemical equations. I like to include it though. This would be the activation energy of the reaction. So this will tell you at above what energy particles can start to partake in this reaction. And then another way of writing this is if your reactants are not the same as your products, you could have different products from reactants. That's what this Z here is. And so we will often describe the reactants as in terms of an incident and a target species. And generally speaking, the first participant is going to be the incident species, and this is usually going to be a plasma particle or a charge carrier in general. And if we ever later on, you'll see this, but whenever we write quantities that are related to the reactants, we will give it the quantity as subscript 1 if it's referring to the incident species, and a subscript 2 if it's the target species. And the most important quantity we can get from the reaction is the reaction rate itself. So it's telling us how often this reaction is occurring per unit volume, per unit time. And it's going to be equal to the product of both of your reactant densities in 1 and in 2 here, as well as the reaction rate coefficient, K sub I here. And Charge Plus offers the multiple ways of computing the reaction rate coefficient, depending on what reaction data the user can find and provide to the solver. And from this reaction rate, we can get all the other quantities of interest, such as the rate of changes in the density, energy, and velocity. And so let's go over kind of the formalisms used for computing the reaction rate coefficient. We have 5 in total, but I'll cover the first 4 here as they are equations that reaction rate data is parameterized to. And so the simplest formalism is going to be the constant rate coefficient, where K sub I is just equal to some constant number, which is shown here as a black line in this plot. And so this is going to be a constant, rate coefficient, regardless of what the temperature of the incident particle is going to be. And a slightly more complex version of this just adds a temperature-dependent term here. We take the temperature of the incident species in units of Kelvin, divide by 300, and raise it to some power. And this gives you the curve shown in red. And these two formalisms, the constant rate coefficient and the temperature-dependent rate coefficient, these are commonly used for reactions that only involve ions and neutrals. And then a more complicated formula that's a bit more general is the Arrhenius formalism, which uses the Arrhenius equation shown here, where we still have A sub I, and then we also have the temperature in units of Kelvin raised to some power. And then we also have this exponential term where T sub I is one of the parameters supplied by the user. And this will can give you a shape that looks like what is shown in the blue curve here. And so you can see how it can both increase and decrease in magnitude. And so this formalism will typically be used for reactions that involve electrons, specifically electron inelastic reactions. And there's also a fourth formalism known as the Townsend rate formalism. The data is hard to find for this, so I've, for the sake of time, opted to not include it here. But that is one of the formalisms available to you. And then the final formalism that we have, the fifth one, is uses cross-section data to compute the reaction rate coefficient. So how do we do that? Well, we have this very complicated and gross-looking formula for doing so. That involves an integral of your cross-section data, sigma sub I of E. And then all the rest of the other terms come from the distribution function that we talked about earlier. Now, this integral can be expensive to compute, so a preprocessor is offered that can pre-compute these rate coefficients for use later on in the simulation. Now, cross-section data is a physically weird quantity because it has units of area but represents a probability of an interaction occurring. And to understand how an area could represent a probability, the best way to think about it is as if it was a target. The larger the target is, the easier it is to hit. So that's can be how area is related to probability. And then in terms of how the cross-section changes with energy, typically you will see that it becomes smaller with increasing energy. And an explanation for this comes from relativity. Relativity tells us that the faster or the higher our velocity is, the smaller distances become. And so at those higher velocities, your links will contract, and so the cross-section becomes smaller because of that. And we also, within this own formalism, we offer two different approaches, continuum-based and particle-based. Particle-based would be the most accurate, but it's also more expensive than continuum-based. And when it goes to compute this reaction rate coefficient, we need to know some information about the incident species, such as the temperature of it. And so that's really where the difference between these two approaches comes in. The particle-based uses the actual individual temperatures of macroparticles within a mesh element, and you can you'll have multiple macroparticles within any given mesh element. And then the continuum-based, what it does instead is it will actually take those macroparticle quantities and convert them to some continuum data that is then used for computing this reaction rate coefficient. And here's just some examples of some cross-section data for N2. And so here you'll have your two elastic reactions are up here at the top. These are typically always going to be your most dominant reaction, except for at really, really high energies. We also have a whole bunch of excitation reactions shown in red here. Our ionization reactions are shown in blue, and there's a couple of different ways that we can do the ionization here. And then finally, we can also split apart the N2 molecule into two free nitrogen atoms. This is called dissociation, and this is shown in the orange line here. But the electron elastic cross-section here gives a good idea for why the Arrhenius formalism is good for inelastic reactions. It's just because it can't resolve these what are called resonances right here. And so if you use the Arrhenius formalism for the electron elastic reaction, you would kind of skip over the contribution from these resonances. All right. Now, how do these reactions actually update our plasma and fluid quantities? Well, before we can do that, we actually have to cover our two basic types of reactions, which are going to be elastic and inelastic. I've made reference to these before, but I haven't actually explained them. But so here's the explanation. So an elastic reaction is one in which momentum, energy, and density are conserved. Now, usually when we talk about elastic reactions, density conservation isn't brought up. But because we're dealing with chemical reactions, we do have to invoke density conservation in order to characterize this some reaction as elastic. And then for inelastic reactions, momentum is conserved still, but energy and or density is not conserved. You could have a reaction in an inelastic reaction in which momentum and density are conserved, but energy is not, or you can have one in which momentum is the only quantity that's conserved and both energy and density is not conserved. But for us, the big difference between these two reaction types is going to be with how we compute the change in energy. And so I said that, but when we for the density update, it's pretty much going to be the same for either elastic or inelastic reactions. Although, of course, because your densities aren't changing for elastic reactions, you're also not going to have your density update is going to be 0. Anyways, the rate of change in the density is given by this equation here. We have our reaction rate, the capital K sub I, multiplied by this other quantity, which I've written as del sub I. And so this is going to be the change in the particle densities per collision. If we go back to the previous slide where I have some examples here, take this second inelastic reaction right here, where we're ionizing into N2+. We can see that we're producing an additional electron, and that is exactly what the del is going to be. So if we just take, basically, the general idea behind computing the del is if you take your molecules on the right-hand side of your equation and subtract them from the molecules on the left-hand side, you'll get your changes. So we can see, electron is changing by +1, N2 itself is changing by -1, and then N2 plus is changing by +1. And those are the del values for this reaction. And then so for the energy, the general equation that we'll use for the total energy update is going to be the reaction rate multiplied by the change in the energy for every collision. And for inelastic reactions, this delta E is pretty simple, pretty straightforward. It's just going to be the activation energy of that reaction. And then for electron elastic, this delta E comes from solving your conservation, momentum, and energy equations. And then for ion elastic, we actually set this delta E to 0, not because energy is not being transferred, but because we're actually going to be transferring that energy through the velocity instead of just through the energy itself. And because your energy and velocity are tied together, you only ever need to increase 1. But yeah, so as I mentioned, your ion elastic reactions will update the particle velocities, and this is the only type of reaction that will lead to a change in the velocities, at least for now. And the reason why your ions will change the velocities, both their own and also the whatever species are interacting with. The reason for this is because their motion is very directed, whereas the electron motion is not. It's much more random, and so the momentum contributions from all the electrons that are colliding with some target species would cancel out with each other because of the random directions. And so these equations that I've listed here are just going to be the changes for a single reaction. That's what the subscript I here represents. By the way, the subscript P here represents our species number. And if you wanted to get the total changes, then all you need to do is just sum the individual changes from each reaction. So if we wanted to get the total change in density, we would have this quantity for every single reaction, and we could just sum them all together to get our total rate of change of density. And these changes here and these rates are applied to both the PIC and the fluid solver. This change in total energy gets converted to a temperature for the fluid solver and is plugged in as a source in the temperature equation, and then the density and velocity terms here can be plugged directly into the respective fluid equations. And then also we can come up with the conductivity for our plasma. And so to do this, you'll want to compute a mean free path for every single reaction, and then summing those together to get the total mean free path, you then use that to compute what's known as the mobility of the species. You can think of this as being a quantity that's kind of similar to viscosity, except it has the opposite behavior. So a higher mobility means that your plasma can move around more freely. It has less resistance to moving around. And in fact, that even comes into play with our conductivity, because our equation for the conductivity is just going to be the product of the species charge, density, and its mobility. And that is the conductivity for that specific plasma species. And to get the total plasma conductivity, you'll just add up the conductivity of each individual species. But typically, you will see that your electrons are what dominates this conductivity, by the way. And so here I've tried to break apart the phases that are occurring within these discharges and what we can learn from them. So phase one is kind of more just an initialization phase. Nothing's really going on. You're really just more so just charging up the electrode, kind of getting your your electron temperature, which is shown here in red, up to kind of the starting line. And so I guess before I get into this, I'll explain this plot real fast. So this is from an example model, which we'll actually see in a later slide. The top plot here is just showing the potential on the cathode, and then this bottom plot is showing the plasma properties for the electrons. And so the blue line represents the density, with the y-axis on the left-hand side here showing you the values. And then the red line here is the temperature, with the y-axis on the right-hand side showing you the values. And I've plotted the max and average electron temperature because before the discharge has occurred, which is signified by this drop in temperature and also in potential, before the discharge has occurred, the max temperature is representative of the plasma as it's forming. But then once the discharge has occurred, the average temperature is representative of the plasma. Anyways, as I mentioned, the first phase here, we're just pretty much charging up our system, kind of initializing everything, and we can see our electrons will just get what I'm calling the starting point of its temperature. And then we enter phase two, where we start to see some ionization, but it's a very small amount. And so within phase two, your fields are strong enough to finally overcome the energy lost due to the reactions, and so your electrons start to gain energy, and start to, as you can see here, we start to gain energy, and we're getting to the point where we can start really ionizing the gas. We do see a little bit during this phase, but it's a very small amount. And then finally, we reach phase three, where ionization really kicks off, shown by this sharp increase in the electron density. We'll also see at this time that our conductivity is increasing, and once it reaches some critical value, our potential drops off. Once the potential drops off, your electric field strength is reduced. And so now your plasma is losing a lot of energy because it's still undergoing reactions and losing energy because of that, but now it's no longer getting as much energy from the electric fields due to its decreased strength. And so that's why you'll see the temperature drop off. And once the temperature has dropped off, you'll see that ionization also stops. So your density stops increasing. And then what follows is some small period of stabilization where your temperature kind of evens out, your density might settle back down to some nominal value, and then your potential also evens out a little bit. And then finally, we've arrived into phase 4, and this phase 4 exists all the way to the end of time. And this is for our large-scale effects, such as heating of the gas, as well as the recombination of the plasma itself. So extinguishing of the arc, should that occur for the model. All right, so that was all good and dandy. You see how the solver works in action, but now it'd be nice to see some actual results. So that's it's exactly what we'll do. And this will also be a nice way of introducing you guys to our UI elements and also kind of how we generally set up these discharge simulations. So for this, I'll be showing you guys this very simple model that I'm calling Passions model. It's a parallel plate setup where your plates are 12 millimeters by 12 millimeters by 3 millimeters, and there's a 5 millimeter gap between the plates. A DC current source is used to drive the cathode, shown in black right here, and the anode, shown in red right here, is grounded. This gap is filled with nitrogen gas. Although any other gas or mixture of gases can be used, nitrogen was used here because it is a gas that we are very familiar with and very comfortable working with. The initial conditions are shown below. The main point here is that our gas was initialized at an atmosphere pressure at 300 degrees Kelvin. And the goal of this model is to be able to get a breakdown voltage that agrees with Passions law. For anyone that's unfamiliar with Passions law, it's simply an equation that tells you what the minimum breakdown voltage of a gas is going to be for a given pressure and gap distance. And so I won't really show you all the reactions because there are quite a few of them. But I just wanted to show kind of the screen so you can see how reactions are defined in the UI. But also, EMA will be able to provide plasma libraries for commonly used gases. We currently have libraries for nitrogen, hydrogen, cuban nitrogen, methane, carbon dioxide, and I believe we're working on one for SF6, although we might have also finished that one by now. And then for any other gas you want, we can provide limited assistance and support, kind of telling you guys where you can look for this kind of information and that sort of stuff. But for this model in particular, for this nitrogen discharge, we're considering 6 species in total. We have 3 charge carriers, which are going to be our electrons, into positive ions and then in positive ions. And our neutral species are going to be the base, just nitrogen gas, the free nitrogen atoms, and this other molecule here, which we write as N2 star. This is what's known as a metastable excited state. So as I'm sure everyone's familiar with, molecules can be excited due to electrons hitting them. And some of these excited states will last for a very long time. They won't jump back down to their ground state. And those are what's called metastable states. For the reactions that are included, there's 49 in total, and it includes the electronic excitation. So this is electrons hitting neutrals and exciting them, dissociation, ionization, and recombination. And so here are the results that we get. And so these are actually what we saw earlier. So this particular model simulated a breakdown voltage of 20.2 kilovolts. And the expected breakdown voltage from Paschen's law was about 19 kilovolts. So we get a 6.3% error, which is pretty good. Also, additional fine tuning can be done to get this model closer to the Paschen's law. But at the end of the day, Paschen's law only tells you the minimum breakdown voltage. It doesn't actually tell you what the breakdown voltage will be for your setup. It just tells you the absolute minimum voltage you can have for breakdown to occur. But you can, of course, break down at higher voltages. And then here's the animation of the electron density. And there you can see it form. It does happen very quickly. And but you can notice that the discharge will form along the edge of our cathodes. We're looking here at a cross section of our gap, and it's about halfway through the electrodes. And yeah, you'll see it kind of form initially here between the two edges, which is where we expect it to occur. In this region of space, our electric fields are going to be enhanced, so we would expect the discharge to occur here. Aside from that fact, we will also see that the density peaks at about 3 times 2 to the 21 particles per cubic meter, and this is going to be the expected magnitude, where that expected magnitude comes from one of our references, which is the NRL plasma formulary. You can also take a look at electron temperature here. And so, yeah, you see the temperature kind of get to a high point about 4.5 EV or so here in the center, right before the discharge has occurred. And then once it's occurred right there, the temperature drops off and settles to about 0.1. And this is an acceptable range, again, based off of that NRL plasma formulary. We expect our plasma temperature to be on the order of about an EV to a little bit less than that. So this is within a range that we would expect. And so aside from that discharge sim, we, of course, can also do some PECVD modeling. And this will highlight some other features that we have, which includes the sheath formation, which is a region of net charge that is developed when a plasma interacts with a solid. And then we have also actually validated this chamber. So this is what's known as the GEC chamber. It's a standardized PECVD chamber with a lot of work done on it. And so yeah, we can validate to literature, and we show very good agreement with literature in terms of our electron density profile here. But there's other quantities that can be studied that weren't talked about so far. And this is going to be, the temperature is going to include the temperature that the background gas reaches once the discharge has formed and starts to heat the gas. While we can simulate this, it's a long time scale effect, and that's why it wasn't included in the example results. This heating would also cause the arc to propagate, which can be simulated in Charge Plus, although this exact behavior has not been vetted yet. And we can also model arc extinction, since we can model recombination. So you can be able to know if your arc will extinguish itself once it forms or not. And then related to that arc extinction, we can also simulate restrike. So when an arc extinguishes, there will still be some leftover plasma in the gap, and the background gas might have an elevated temperature. And both of these in combination can cause another discharge to occur at a much lower voltage, or at a lower voltage than the initial discharge did. And so Charge Plus can be used to study that as well. And so the final thing we have here is just future development. We plan to continue to expand our discharge capabilities, and the features we plan on addressing and adding over the next year or so is going to be an ablation model. So your plasma will remove material from solids. The ablation model will be able to simulate that. Also adding in the ability to have moving geometry. So like we could simulate the actual opening of a switch breaker, and how that would draw the arc in that case. And then finally, another thing we plan to add is the temperature It's going to be actually simulating the temperature of solids, which will kind of play into the ablation model and play into a couple other places too. But with that, you'd be able to know, like if you had a discharge occur, in some, let's say a circuit breaker, for example, and you'd be able to figure out the temperature that the nearby components would reach to see if they're at risk of, melting or something like that. And then here are my references that we pulled from for this presentation here. And that is all I had. And we went a little over time, but.
Okay. Well, thank you, Jacob. That was a very informative presentation, and we received many questions through the Q&A feature in the Teams webinar. So if you have not found that feature already, please look for it, and you can submit any questions through that, and we'll do our best to get through them. Let's start out with the first question here. So the first question is, can only 2 species participate in a given reaction, or do reactions exist which include more participating species?
Yeah, so you can have more than 2 participating species in a reaction. And these are called like 3-body reactions. However, they're very uncommon for plasma chemistry. Usually, if you do have a 3-body reaction, it's only occurring between neutrals and not with like the plasma and the gas itself. So we tend to ignore them for now, but we do plan on in the future adding support for 3-body reactions.
Okay, thank you. Next question. Can the simulation be used for RF plasma? I assume they mean radio frequency plasmas.
Yes, it can be used for RF plasmas. The main difference here between an RF and a DC plasma is going to be how the conductivity is computed. In the RF case, you'll have a slightly lower plasma conductivity, which we are planning on adding support for in the future. But more importantly, when it comes to RF plasmas, what you really care about is not so much, well, you do care about the conductivity, but you care more about any sort of power reflection that can occur. And that is something that we can simulate, yes.
Okay, great, thank you. Next question. Can you comment on how to model vacuum discharge and how that would be affected by dust and surface conditions?
Yeah. So for vacuum discharges, you obviously have no gas to ionize. And so the discharge, the electrons in the discharge come from someplace else. And in fact, what occurs for vacuum discharges is your electric fields will reach such a high magnitude, usually in the order of like 10 to the 7 volts per meter or somewhere around there, where they can just like rip electrons off of the surface of conductors, freeing them from the metal and launching them into space. And so that's how the electrons are produced for vacuum discharges. And we do have those emission models in Charge Plus. We have a field emission model, which was what I just described. And there's also a thermionic emission model, which is the same thing, but if your conductor is at some elevated temperature. And then as for how the dust and surface conditions are going to affect this, well, both of those things are going to affect the electric field on the surface, and so that's how they can affect the vacuum discharge. If they usually will increase the electric field locally, so that can lead to a vacuum discharge occurring at a lower potential.
Okay. And I think we have some active research in that area on one of our contracts with the U.S. Navy.
That's right.
For creepage and clearance topics. So yeah.
That's right. Yeah, we're investigating the effects of surface roughness and how to compute the enhancement factors from them. Yep.
Okay, next question. Would the plasma conductivity be the same for a plasma driven by an AC signal?
No. So your AC plasma would have its conductivity reduced by a factor that's proportional to frequency of the driving signal. Currently, we don't have that implemented into our plasma conductivity calculation, but it's something we plan on adding in soon. And the difference, even though I say there is a difference, it's a fairly small difference. They're still very close to one another in value.
Gotcha. Next question. How many reactions can I expect to have in a discharge model?
Yeah, so that largely comes down to what kind of gas you're modeling. So if you're going for a more simple gas like H2 or N2, so these simple diatomic gases, you could have like 40 to 70 reactions in your model. But then for your more complex gases such as methane and SF6, you really start to see large number of reactions. I think like for those two gases in particular, I want to say number of reactions is close to like 160, somewhere around there. So yeah, you can definitely get quite a lot of reactions in the models.
Okay, very interesting. Question that just came in. How is partial discharge in dielectrics modeled?
Are you talking about a solid dielectric? Um,
I would
well,
assume
I guess
so.
I get
That's
okay.
not specified, but I would assume so.
Yeah, so for solid dielectrics, we actually have a different a model for that, which uses stochastic treeing. Um, and in that case, it's what we'll do is we'll check to see if some node has or some portion of your solid dielectric has a electric field that exceeds the dielectric strength of your material. If so, those that region is broken down, and it could cause further regions to break down, or it might not. It all depends on your setup. But yeah, regardless, you'll be able to model a partial discharge in a solid dielectric.
Okay. Let's do two more questions and then we'll need to have some time at the end to wrap up. So second to last question. If the conditions are met for corona discharge, does it follow that there would be arc discharge if given a ground/connection point?
Yes, 100%. Yeah.
Okay. And let's see, here's a longer question. If I wanted to reduce plasma down to a lumped parameter, could your particle and cell solver determine the impedance of the lump? And then it goes on to say, I'm interested in determining plasma grounding behavior. Are there any tools or methods to do this?
That's a very good question. Um, so they do report on the plasma conductivity. So you can use that to get a lumped impedance for your plasma. As for the other aspects, so your plasma is actually going to be an RLC component. It will have both all resistance, conductance, or capacitance and inductance as well. Although typically we care about the resistance and capacitance. And as for that capacitance, I don't believe we report on that, but that is something we can look into in the future.
Okay. Well,
Yep.
there are a number of additional questions, but we're not going to have time to get through all of these. So I just want to take some time to wrap up here. First of all, again, thank you, Jacob, for this really nice presentation. Um, any of the questions that we did not answer live here today, we will address those via email following this webinar. You will also be receiving an email from us with a link to the recording of this presentation. Feel free to share that with your colleagues. If you have any questions about a particular section, please feel free to reach out through the ema3d.com website. There is a contact us link on the website, and we will get that and we will route it to the appropriate person to answer those questions. And then just wanted to mention here briefly, next up in the EMA Solving Electromagnetic Challenges webinar series is a webinar on GPU accelerated ray tracing for radiation dose mapping, and that is going to occur on September 15th. I'm sorry, September 25th, so just a little over a month from now. So thank you very much for your time and attention today, and I hope you have a great rest of your day.